As you like.
Okay, so now you are going to explain the caustic of the angle, right?
Of the corner, yes, and its relation to tropical angle.
And the relation to of the corner, and its relation to the concept of tropical angle. Perfect. Let's go on. The screen is yours.
Okay. So do you see the screen? So this is where we were last time. I defined a tropical angle of a rational corner. And if this corner is not a half plane or array, if it's a proper corner, then the tropical angle of if the rays have rational slopes belongs to the rational points of the circle, in a sense like Q mod Z. And I told that there is inversion formula. This definition of the tropical angle depends on the ordering of the rays, and that the transformation is from P over Q to Q prime over Q, where P in Q and P prime and Q prime satisfy this condition. So like one way to think about it is that the first parameter of the tropical corner is Q, and P is an invertible element in the ring Z. So P is an element in the ring Z mod QZ, and this Q prime is the inverse. So
That's right. That's right. That's right.
And there was some mysterious conjecture that I suggested that this inversion should be related to some continued fraction. Indeed, it's the case, but it's not the continuous fraction I was thinking about. So this continued fraction, I thought it should involve the multiplicities of the tropical Caustic. So here. Like M1, M2, M3, etc. So I thought like you do something very silly, you just form the continued fraction with this formula, with these multiplicities, and this should give you tropical angle. Well, this is very wrong, but there is a way to overcome this. Also, this is why I was speaking about the inversion of continued fraction, because if you change the role of the rays, this is just switches the order of to the reversed one for these multiplicities. Okay.
Nevertheless,
Yes.
it's a bit mysterious that that the formula of inversion is true, for the continued fraction.
Yes, you'll see very explicitly. So, like, why I thought about this at all? That there should be relation. There should be some way to go from tropical Caustic to this tropical angle. So, tropical angle is the only parameter of this corner, and I thought that there is an analog of the following statement: if omega is a compact convex subset of R2, then going from omega to C omega to the Caustic as an abstract curve, well, tropical Caustic in the interior, this can be inverted. So in this sense, I was telling that the moduli of the tropical Caustic are the coordinates on the space of compact convex domains.
Question: this can be inverted or has a section? I mean, is one-to-one or just has a section?
So this is a little bit subtle in the sense that yes, well, you should be very specific by what you mean an abstract tropical Caustic. So it remembers the germ of the terminal singularity and the moduli. And then you can restore your domain up to SL to Z action. So you don't restore it physically. So you restore its image in the quotient by the SL to Z.
That's right. Okay.
So
Okay,
yeah.
very good.
So this statement is wrong if compactness is dropped. And it's wrong already for corners. So I've never systematically considered examples, and to answer this question about the relation of the tropical angle and the tropical caustic, I attacked it just by considering not a very massive amount of examples, but some considerable amount of examples, and I very quickly found that this statement is wrong. So let me just explain you what is the recipe. So without any proofs, I'll just tell you very quickly what you should do. So first, let me draw. This is the corner. Let's say it has M1, M2, M3, the multiplicities of its rays of the caustic. The caustic will be just the union of rays. And abstractly, the information about this tropical curve, if we exclude the apex, the tip of the corner, is just the ordered set of these multiplicities. Okay, and so it is not enough to know just M1, M2, M3, etc. to restore the corner or the tropical angle of this corner, which is the only invariant of it. So, but the question is, what is enough? And I tell you. So actually, the solution is to look, so refine the information M1, M2, M3, etc. By looking at the canonical flow. So in the compact case, canonical flow and the tropical caustic is the same thing. There is no difference. So, but here, so let me draw what will happen. So you, at time one, let's say. So you have the copy of this ray. Then you have something small here, something small here. Then you have copy of the second ray.
Okay, yeah.
And let me call this N, let's say N1, or even better L1. L1, L2, etc. So these are the length of finite edges at time one. Okay.
Perfect.
So this is some extra information. The caustic in general doesn't know about this. And so let me tell you what sequence you form. You start with 0, etc. 0 of.
I'm a bit confused though.
Yeah.
Here we are really in geometric world, not in cellular automaton world, right?
Yes.
So, yeah, the flow was defined with the inequalities and so on, wasn't it?
Yeah. Yes. It's so the tropical caustic is the tropical curve defined by some tropical polynomial or tropical series more generally. And this is the boundary. No, this is just exactly the level set at the value 1 of this tropical polynomial.
That's right. That's right.
And the
It
tropical.
was that big.
So
thank you.
so let me consider a concrete example maybe. And we will finish just with that. So, and the idea will be clear. So if you take the corner with tropical angle equal to 3/7, so that's already quite some angle. So what you're going to see, well, it's an angle, and you are going to see one ray with multiplicity 1 and another ray with multiplicity 3. Okay, and
could you explain this again? Could you explain this race again and just slow to this?
No, I can't explain it. I can't explain it quickly. So this is another topic. Just for your information, if you take tropical angle with of 3/7, then you're going to see one ray of multiplicity 1, other ray of multiplicity 3, and that number n1 is equal to 1. So there is only one finite edge. Okay, so what you do now, you form a sequence. So you start with just a single one. Okay, so the yeah. So
back, yeah, we're back. So you said, just for your information, if you take
okay.
a tropical angle.
Yes, this is just to consider an explicit example. So in general, you start with 1 minus 1 zeros, so there is nothing. Then you have 1, and then you write 3 minus 3 minus 1 zeros. Okay, so more generally, you have two sets of numbers. You have m1, etc., and n1, etc. So this is n1, this is m1, this is m2. Okay, and so the sequence you form is as follows. You start with m1 minus 1 zeros, then you write n1, then you write m1 minus 1 0, m1 minus 2 zeros, then you write n2, okay, and this sequence I call s1, etc. Okay, so this is s1, this is s2, and this is s3. And so the recipe I tell you is that tropical angle is equal to the following chain fraction. You start with 1, you divide by 1, then you write s1 plus 2, and then surprisingly minus 1 over 1, s2 plus 2, again minus, and etc. Okay, so here in particular, you see that you should write 1 over 1 plus 2, because this one is 1. Then you take minus, then you write 1, 2, because it was 0, then minus 1 over 2. So I 1 over 3 minus 2 over 3 will be equal to 3 over 9 minus 2 will be 3 over 7. So, to wrap up, it is the right sequence to consider is a refinement of sequence of these multiplicities of in this case it's 1 and 3. In which sense it's refinement? It's a bigger sequence which includes the length or if you like, these are the speeds of the finite edges in this canonical flow, and m1 and 2 etc. the multiplicities of the caustic, they serve as the numbers of zeros in this sequence, but minus 1. So in a sense, you should think that I explain why. You should think that multiplicity 3 ray is actually 3 rays in parallel. And in this case, you have these two finite, between these three rays, you have only two finite number, two finite edges, which doesn't change speed at all, which have speed 0 at the flow time 1. Okay, so that's it. That's how you do how you construct, if you like, the multiplicities of the tropical caustic from the tropical angle. Well, okay, let me just spend one last slide how you do it from the point of view of the algorithm. So you start with alpha. Alpha, this is tropical angle, and from alpha, which I assume is strictly from 0, 1, you do alpha minus 1, and unusually to this chain fraction business, you do the upper rounding, the ceiling, which
the upper
belongs,
one.
yes, which belongs to 2 plus infinity intersection with integers. And then you do I don't know, alpha 2, let's say this was alpha 1. You take alpha 2 to be equal to, and this is S1 minus, yeah, S1 minus 2. S1 plus 2. So this is the number you are hunting for, S1. Then you do alpha 2 as this alpha 1 minus 1, upper ceiling, minus alpha. And this is again from 0, 1. Then you take alpha 2.
You repeat.
Yes, exactly. And this is going to be this S2 plus 2. And you do etc. And to find the multiplicities of the caustic, you look just for zeros. Okay, you look just for zeros in this sequence, and my bamboo has crashed. So yeah, I wasn't able to write it. Let me restart it. Is it was it clear? This is just the recipe, and it explains really this chain fraction business like with reversion. So this is indeed if you reverse the chain fraction, you get this inverted element in this ring Z mod Q Z.
Fantastic. Fantastic. Could you put on the screen again the story?
Yes.
Yeah.
So to find the multiplicities of the caustic, look
Kill
for
this little Skype window, you know, just
yeah.
close it down.
Look for
Great.
the
Of
numbers,
zeros.
yes, of consecutive zeros. So just 1 0 already means multiplicity 2. No 0 means there is some edge of multiplicity 1.
That's right.
And
Very good.
yeah. Okay. So we wrap it that. Well, we wrap it up. So we
Yeah. Very nice. Very nice story. Anyway.